Okay, so we're moving on to the second chapter of the textbook, which is going to be about work, energy, and power. So this is going to be the first of two sort of mini chapters of work, just defining work and getting used to working with work. Yeah, using that in your equations, using that as part of problems. So I think to start off with, I just wanted to make sure we're all clear on what we mean by work, because you may have heard it already in physics. So even though I technically haven't told you what it is yet, you might have some idea if you have had physics lessons, or maybe you've heard it somewhere else. But I've given you 6 examples of situations, and for some of these there is work being done, and for some of these there is not work being done. And the question is, for which of them is there work being done? And I'm using work in the strict mathematical / physical sense. Okay, so have a think, pause, just read them quick. Which ones do you think they are? Okay, and as it turns out, the ones that have, oh, poor colour choice. The ones that have work being done are 3 and 6, and only those two. And in the others, there is no work being done. Okay, I'm going to define work on the next slide, just in case we're not quite sure what it is. But I'll just give you a rule of thumb for now. If nothing is moving, then no work is being done, right? For work to be done by a force, something has to physically be displaced, it has to move. So if you apply that rule to these examples, we can see that if I sit on a chair and there's a book on my lap, if none of that stuff's moving, I'm not lifting up the book is stationary on my lap, there's no work being done. Number 2 in particular is one that gets people. If I'm imagine I've got like a I don't know what you call it, a big, one of those bars with the weights on either end, dumbbell or something. So you hold it up above your head, and it's not moving. There's no work being done. Not in a physical sense. So it might seem weird because you'd think, if I'm holding something above my head, I feel it, right? I have to actually make an effort to hold it in place. If I just give up and I sort of relax, the weight's just going to drop. So it feels like I'm pushing against it. I mean, you are supplying a force, and gravity is counteracting it. But unless the weight is actually moving upwards, or slowly falling downwards, then no work is being done, right? And that ultimately just comes down to what the definition of work is, okay? Which requires that a force causes something to move. So even though you might use work in a layman's sense, like in an English language sense, you might say, this is a lot of work holding up this weight. Sure, but in terms of physics and mathematics, no, it isn't. There's zero work being done. You're not doing any work, which I guess is the basis of a lot of these sort of mathematical jokes. But it is a point of confusion. So when we talk about work, something has to move. So then in 3, you're dragging a box along the floor, so work is being done. On 4, you're pushing a car stuck in the mud, but the car doesn't move. It's just like the weight being held above your head. It's a similar idea. Sure, it feels like you're putting in a lot of effort, and you can use the word effort here. It's a lot of effort to push this car, and it's still not moving. But if it doesn't move, there's no work being done. 5, I'm assuming it's a fairly stable wall, and it doesn't move when you punch it. You punch the wall, there's a force, the force of your punch. There is energy being transferred in some sense, but no work's been done because the wall has not moved, okay, on that impact. And then finally, doing a push-up, there is work being done. The work here is that you're on the ground, so imagine you're lying on the ground. Let's say you're completely flat on the ground, hands either side, and then you push the earth or the floor and you lift yourself up. So your body has moved. You have lifted your body up from being flat on the ground to being elevated from the ground a little bit, or maybe a lot, depending on how good you are at push-ups. So that is work done. In the case of 3, the work done has caused the box to have kinetic energy, which is a topic we'll get onto, but you might have heard that term before in physics. And in number 6, doing the push-up, the work done has given you increased gravitational potential energy. Again, something that we'll get onto a little bit later. But you've got a preview there of what of how we might use those terms. Okay. Cool. All right. So with hopefully those misconceptions got rid of, let's look at the actual formal definition of work. So when we talk about work or work done, it's always done by a force, right? So we associate, so for every force which is causing some sort of interactions, sometimes there's work done and sometimes there isn't work done, but we can pick a force and we can then ascribe to it either some work done or not. So work is not done by people or objects. I mean, maybe indirectly it is, but ultimately you assign work to a force. Okay, let me just write that down then. So let's say work is done by a force. Okay, and that force could be the force of gravity, it could be the force of you pulling something, it could be a tension force, it could be you pushing something. So in those examples we had, those 6 examples, there were forces presumably going on, but only for 2 of them did those forces actually result in movement. Okay, so work is done by force. And then how is it defined? Ultimately, it's kind of okay, let's give you the full definition. So work done by a force, it's a product of 2 things. It's the product of hang on, let me just clarify. Work is done by a force, let's say, on an object. Okay, because forces ultimately they act from an object A to an object B, right? So it's this object B, they act on an object. Okay, so now with that defined, the object is defined. Work done by force is equal to the component, I just want to get this right, the component of force in the direction of motion of the object. So this is the really general full definition. We will simplify it in a little bit for easy cases. Multiplied by the distance that the object moves in the direction of the force. Okay. Now, that's sort of like the general case, which works for 2 dimensions, 3 dimensions, and so on. Let's just write a simpler version, which is the one that's often quoted, which is for 1 dimension. And in 1 dimension, it's simply work done is equal to force times distance. Okay, and that's the way you're generally given it, and the way you may have heard it before. Work done is force times distance, but distance of what? The distance moved by the object. Force, what force? The force acting on the object, and the work done by what? The work is done by the force. However, you want the more general version, because once you start working on 2D and 3D, you need to have this version of it in your minds. Okay. So, for instance, the case where let's think of the case where we're pulling a box along the floor. Okay, if I'm pulling a box along the floor, if I wanted that to be one-dimensional, a one-dimensional problem, that must mean I'm pulling it in such a way that the direction of my pulling is along the motion of the box on the floor, so it's parallel to the floor. If I'm pulling it on a string at an angle, then you'd have to use the more complex version, which is this one. But if we treat it as a 1D problem, then it's going to just be a force that's horizontal to the floor. If I take that force and I multiply it by how far I move the box, let's say I pull it a meter, or maybe 1 is a bad number, let's say I pull it 5 meters, multiply 5 by the force that I was applying, assuming it was a constant force, and I've got the work done. Okay. Final thing then that we want to clarify is the units. What are the units of work done? Let's just have a think about that. So the units of work done are joules, which you can see I've written it as the title. So joules measure energy, and work done is effectively a transfer of energy. It's a bit like how you've got momentum, and then impulse is a change in momentum. In a similar way, or analogously, you've got energy, and then work done is kind of like a transfer of energy. Okay, it's energy of in one form gone to another potentially, and it's been transferred by this force. So we can just say work done is measured in joules and be done with it. However, at this stage then it's useful, I think, to see if we can figure out what joules would be in terms of base units. And you actually have enough information now to be able to do this by yourself, to find joules in base units. So perhaps you can give it a go. But if you're not up for trying, then let's take a look. But hopefully you have time to have a think about it. So I'm just going to write it very informally. Work done, W, equals force times distance. And I'm also then going to make use of F equals ma. Force is also equal to mass times acceleration. So therefore, work done is equal to mad. And then if we consider the units, so let's not get confused with, you have to be careful here because there's m being used for mass, and then we also use it for meters. So I'm just going to write it in everything in a different color. So we have the units being mass being kilograms, acceleration a is meters per second squared, and distance is meters, right? So we've got this situation going on, which therefore gives us kilograms meters squared per second squared. And that is the base unit of joules. That's what a joule is, right? A joule is the same thing as kilogram meters squared over seconds squared. Okay, and we've derived that by using two of our formulas that we now know. This we already knew, and this is potentially we knew or might be new to us. Okay, so generally speaking, you're just going to use joules. You're not going to write kilogram meter squared per second squared, but it is good to know what the base units actually are, because it might help you convert or double check certain formulas you're using are consistent. Because within physics and mathematics or mechanics, your equations, if you're multiplying, adding values together, the units should always align. And the way you check that is by putting everything in terms of base units. Cool, all right, so that's work done. Formally defined. Let's look at some examples and then we'll do some questions. They'll be quite basic to start with. In our part 2, we'll look at some more complex ones using friction. But let's get the simple stuff out of the way first. Sorry, one more slide before questions. which is a specific category of work done against gravity. Let's just talk about this for a moment. So we said work done is associated with a force. Now gravity is a force. So if I have work done against gravity, then what that is effectively saying is the work done by a force, not the gravity force, a different force which is working against gravity. A good example of that would be the lifting weights, right? If I'm lifting a weight, why is it so hard to lift this weight? It's because gravity is trying to pull it down. So my force of my arms, you know, however big or small that force may be, that force going upwards is going against gravity, and we can assign a work done to it. So let's stick with one dimension to keep it simple. What is that force, right? How much must I be going against gravity, or what is the force of gravity effectively? If this object has a mass of m, say, what is that force? It's going to be mg, right? So the force of gravity on object mass m is mg. So therefore we're going to replace F with mg. So in this specific case, work done against gravity, we're going to say it's mgd, and then for whatever reason this is always rewritten as being mgh rather than mgd, right? And the reason for that is instead of calling it a distance, it's just renamed, and now it means a height. Because when you're doing work against gravity, I suppose within the English language, you're talking about things going upwards, away from Earth. You're working against gravity, and you're reaching a certain height. I guess it just makes it a little bit clearer, because technically, if I slide a box along the floor, no work is done against gravity, because I haven't moved it in the direction away from Earth. So only if something gains height do you actually do work against gravity. So a box sliding on the floor does no work against gravity. So it helps make that distinction a little bit. So in that sense, fair enough, it makes sense to change it to an h, but it is still effectively a distance. Okay, so that's it. Work done against gravity. Let's just write in purple, have it nice and clear. You just want to remember this. It's fundamental. Work done against gravity is mass times the gravitational constant, 9.8, times h, times the height achieved. Okay? Okay, example time. So a box is pulled 7 meters across a horizontal floor by a horizontal force of magnitude 15 newtons. Calculate the work done by the force. It's easy. So what is 7 times 15? And that's your answer. We're going to write it as joules. Okay, so it's simple enough. I suppose at this basic level, a good thing to do is to just double check that, because the question itself, the arithmetic is simple. So double check that you are making all the correct assumptions you can. For instance, in this case, if you just blindly multiply numbers, yeah, you'll get it right if the question's simple. But what happens if, for instance, we omitted the word horizontal? Okay, if the question was, a box is pulled 7 meters across a horizontal floor by a force of magnitude 15 newtons, what's the work done by the force? The correct answer now is, I don't know, because I don't know the direction of the force. So the key is in the details. You can just assume that everything has been made simple for you, but I'd say a good bit of practice with these basic examples is to think to yourself, which words are there and why are they there? Why does it say horizontal force? right? Would there be a difference if it was pulled or pushed? In this sense, no. In this context, no, it doesn't. It doesn't matter if it's pulled or pushed. So pulled is not so important. Horizontal force on a horizontal floor is in fact important. Okay, because this makes it a one-dimensional problem, and so therefore it is just 105 joules, 7 times 15. Let's look at the next one. Case is pulled across a horizontal floor by a horizontal rope. Case moves at constant speed. There is a constant resistance to motion of magnitude r newtons. When the case has moved a distance of 12 meters, the work done is 96 joules. Calculate the magnitude of the resistance. Do we see the answer? Again, basic arithmetic. Work done equals force times distance. I've written the one-dimensional version. Is this a one-dimensional problem? It appears to be. 96 equals force, in this case is R, the resistance force, times distance 12. R equals 8 newtons. Done. A bricklayer raises a load of bricks of total mass 30 kilograms at a constant speed by attaching a cable to the bricks. Assuming the cable is vertical, important, calculate the work done when the bricks are raised at a distance of 7 meters. Okay, this is a 1D question. It's one-dimensional. They go up 7 meters, so H is 7. The mass of the bricks is 30. And G is equal to 9.8. Multiply those three numbers and you've got your answer. I don't have the number with me right now, so 210 times 9.8, and that's the answer. Let's just think about the subtle details. Does the cable have any weight? It doesn't say. So is the question ambiguous? Calculate the work done when the bricks are raised a distance of 7 meters. So it's not really ambiguous. I mean, it's always, if you're going to be able to have an answer, then you know what needs to be done. However, technically, I would say calculate the work done. A better phrasing would be calculate the work done against gravity by the tension in the cable. And this is implicitly what's being said, right? Which force is doing this work? It's the tension in the cable, right? And why is it doing work? It's doing work against gravity, and that's why you can use MGH. Okay, cool. All right, let's look at the next example. Okay, final one before we do some questions. I think this is a good occasion to do some Pictionary style stuff. So we've got some ice, and you've got a sledge, and then it's pulled a distance of, bad colour, it's pulled a distance of 15 meters by a force of magnitude 27 newtons. And then now here's where we start to differ from our previous problems. The force is inclined at 25 degrees to the horizontal. Okay, so this is not a 1D problem. So let's model the sledge as this black dot here. The force is 27 newtons. It's inclined at 25 degrees. So now if you were to go back and look at the full statement of work done, it's the component of the force in the direction of motion. Which way is the sledge going to move? It's not going to come off the ground. I suppose, yeah, I suppose maybe that is an assumption in itself, but it's not coming off the ground. We're pulling it along the ice, but we're just pulling it at an angle, right? Presumably with a string. So now we need the component of that force in the angle, in the direction of the horizontal. So we're going to find this value here, and that's going to be hypotenuse times cos 25, or cos of the angle. So that's 27 times cos 25. Work out what that is. That's the force, and then you multiply by the distance. So our final answer should just be that the work done is equal to 15, which is the distance, times the force in the direction of motion, which is 27 cos 25. Okay, notice that we only have to do it for the force, not for the distance. Technically, if you were talking about a different kind of distance that wasn't in the direction of motion, you might have to tweak that as well. But for this specific question, the motion was horizontal to the ice, and the distance moved was defined as also being horizontal to the ice. That green line is parallel to the blue line representing the floor of the ice. So 15 stays as it is. But force we've changed. And then again, you'd work out what that is. I'm not actually that fussed about the number. The point is you know how it's done. So you'd work it out on a calculator, and that will be it. You've got it. Cool. So let's try some questions. As I said, they're basic level at this stage. We'll get onto some more complex stuff using friction in the second half. But for now, see if you can just 100% all of the questions on the following couple slides. So we've got 2 pages. They're all very quick fire. See if you can do these 5 here on this first page, and then have a go at those on the second page. You can pause the video now. And you've got your final question there, which we haven't seen an example of. Work done against gravity when you pull something up a slope. Give it a go.